Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.46. It says, an open-ended mercury manometer is to be used to measure the pressure in an apparatus containing a vapor that reacts with mercury. A 10 centimeter layer of silicon oil, specific gravity equals 0.92, is placed on top of the mercury in an arm attached to the apparatus. Atmospheric pressure is 765 millimeters of mercury. Part A. If the level of mercury in the open end is 365 millimeters below the mercury level in the other arm, what is the pressure in millimeters of mercury in the apparatus? Okay, so here I made a diagram here of putting their words in, putting the picture to the words. So you've got this little bit of oil that separates right here, that separates the mercury right here from the reagent, because the reagent reacts with mercury, so you have to have something that separates it. And the reagent is some sort of vapor. They don't give us any more information on that. And it's our job to figure out what the pressure is inside of this pipe, basically. We do know that the atmospheric pressure was given to us here, and we know the difference between the liquid levels of the mercury. But we have to remember that there's 10 more centimeters on top of that that's got some oil on it as well. So first thing I did was I wrote down all of the stuff that we knew, and I put it into standard units. So we've got the height of the oil, which is 10 centimeters. Got the height of the mercury, convert that into meters. The density of the oil they gave to us, density of mercury we can look up. I convert the atmospheric pressure into pascals and write down what the gravity is here. Okay. It's our job to figure out what the pressure is inside of this pipe, and I said that that was P sub G. Okay, so first I drew a line, which is PA right here. I drew a line across PA, you can see in red here, to compare the pressure in the manometer. So at PA on the left-hand side, and then we'll compare PA on the right-hand side, and those pressures should be equal. Okay, so in the left-hand side, we know that PA is equal to the pressure, the gauge pressure that the pressure inside of the pipe, plus the gravity times the density and height of the oil, plus the density and height of the mercury difference. On the right hand side, we know that PA is equal to the atmospheric pressure. Okay, now we have our left-hand equation and our right-hand equation. We can put these two things together and rearrange some of the terms. So we have that PG is equal to the atmospheric pressure minus the pressure head on the left-hand side. And we know what all of these values are. We define them all over here, so basically just substitute all these values in and crunch the numbers. And I got that the pressure inside of the pipe, we know that it should be less than the atmospheric pressure because the column head is higher on the left-hand side than it is on the right-hand side. And then we convert that into millimeters of mercury, because that's what the problem statement asked for. And sure enough, that is less than the atmosphere here. The atmosphere was about 765, and our pressure inside of the pipe was less, 395. Great. Okay, so for part B, when the instrumentation specialist was deciding on a liquid to put in the manometer, she listed several properties the fluid should have and eventually selected silicon oil. What might the listed properties have been? Okay, so I kind of brainstormed for a little bit. There may be more than this, um, but this is not a complete list necessarily, but it's a pretty basic list that you should keep in mind when you're working with a new process. Okay, so first thing I thought of is, because they mentioned this in the problem, is that the chemical needs to be stable to the container, whatever the container is. I would assume that it's stainless steel or iron. It could be some sort of nickel alloy or something like that. It depends on what the reagent is. But the silicon oil needs to be stable to the container. It needs to be stable with compatible with the mercury and compatible with the reagent. So it has to be compatible with all three of those things because that's what it's in contact with. It's also helpful if it's stable in air, and then you don't have to worry about it in when maybe you put air into the pipe when the reagent's not in there, or when you're working on the pipe or something like that. That's something else that you could also have in there. It needs to be less dense than the mercury and more dense than the reagent. So what would happen is if it was less dense than the reagent, well, then it would just kind of float up the pipe and out that way. It wouldn't stay in its spot right here. And then the same thing if it was more dense. The silicon oil, well, if it's not silicon oil, but whatever you put in there, it would just kind of sink through the mercury and end up in the bottom of the tube here. The chemical needs to be insoluble in the mercury and the reagent. So if it's soluble and it forms some sort of liquid mixture either with the reagent or with the mercury, then the properties of the mixture are different than the properties of the pure substance. So you're going to get something very different, or it'll just completely disappear. It'll just soak into the mercury, and then you have mercury exposed to reagent. Or it'll soak into the reagent, and then it doesn't form a barrier between the two things anymore. The oil needs to have a really low vapor pressure. So if the chemical doesn't have a low vapor pressure, it'll just kind of turn into a gas, and then it'll flow out with the reagent. Even if it doesn't react with the reagent, it'll just turn into a gas and just kind of flow out with the reagent whenever you move the reagent around, and then you no longer have your barrier anymore. It needs to be, this is kind of a blend of some of these other ones, but I think it hits on a couple of extra points here. Because you also have to check its own stability with itself. There are some chemicals that go through like a decomposition reaction or something like that. You need to make sure that in the operating temperature and pressure that you're at, that the phase and chemical stability is good for whatever you're using, even with itself. It might be good with mercury, it might be good with the container and the reagent, but if you're operating at a temperature where the chemical you're using decomposes, then you won't have that chemical anymore. It'll turn into something else, and then whatever that other thing is might not have the same properties that you were interested in it having. So yeah, there's a bunch of chemicals that will, if you heat up baking soda, it will decompose, and just look up decomposition reactions, and oils are all organic chemicals face this problem, that when you're operating at higher temperatures, they'll decompose. Some of the carbon hydrogen bonds will break. All right, well, that is it for problem number 3.46. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.